Okay, hello everybody. Thank you for joining the webinar today. And my name is Michael Kwok, as Christina mentioned. And looks like we're just getting to be right on the hour here. So I'm going to go ahead and get started. And this webinar is intended for people with various backgrounds. So there will be some basic fundamental information that you may know already, but I thought that was necessary to provide a complete explanation of the topics that are to come ahead of that. Okay, so I'm going to go ahead and get started now and introduce myself. My name is Michael Kwok. I'm the product line manager for the communications test products at Yokogawa. I joined the company in 2006, close to 10 years now. I started out as the Western Regional Sales Account Manager, covering the Western states, and then in 2010, I became the product line manager or product marketing manager for the communications test products. My corporate experience in the past, quite a bit different types of industries. Started out in actually aerospace industry with Moog aircraft, and was a design and project engineer there. But worked on the flight data recorders or data acquisition equipment. Then also worked with a medical device company, Siemens Medical Systems, as a manufacturing engineer on the manufacturing side. We made that company made high energy cancer radiation equipment. And then I started my fiber optics career at Icon Fiber Optics. Spent about 7 years there, and they made automated optical test equipment like switches, tunable passive filters, and variable optical attenuators, similar to some of the products that Yokogawa offers right now. And then I also worked at this company called Circadian Systems. They focused on a 10G stress receiver tester for optical transceivers and systems, and which they were acquired by JDSU after I departed the company. So with that, I'm going to go ahead and jump into the agenda for the presentation today. Of course, I'm going to introduce, just give everybody a little background on the corporate information for Yokogawa, and mention the definition for OSNR and the importance of it, what is best suited for measuring OSNR, what equipment, what tools, and then jump into the discussion of the basic OSNR measurements using modulated or CW light. I'll talk about the automated measurements that's available in the equipment, and also talk about the single and dual resolution method and why that's important. With corporate background, for those of you not aware, Yokogawa was founded in 1915, a little over 100 years ago now, and pretty amazing. The company started out making electric meters, and you can see in the picture on the right here is a meter from the 1930s, and right now we've been focusing on the test equipment for over 100 years, with 18,000 employees worldwide, $4 billion of revenue, and with global operations in over 33 countries. The most significant acquisition for this webinar is the acquisition of Ando Electric. Some of you may have used, and the OSA picture here was a very popular OSA back in the telecom boom years, the AQ6317 series. Okay. Some of you may recognize the keys. If you have a Yokogawa OSA now, the keys and the front panel is virtually identical, as well as the menu. Okay. And another thing I want to point out is our corporate office for the test measurement division is in Atlanta, Georgia, and we have offices in Houston, Mexico, and Canada as well. The reason for having the office in Houston is because we have a large oil and gas industry there, and obviously that's a popular area for that. So I'm going to jump right into the OSNR definition and importance, why that's important to have a precise method to measure your optical signal to noise ratio. So most of you, I'm sure, are quite familiar with the diagram here showing a wavelength division multiplexer, a block diagram. So just to kind of quickly review that, this is a method to transmit optical signals by combining multiple channels together at different wavelengths, as you can see here. You got channel lambda 1, 2, 3, 4, and up to multiple channels, and combining that in a mux and transmitting that through a long distance of fiber. And then as you're transmitting through the long distance fiber, you would naturally get the attenuation on your signal. So that's important, of course, to amplify that signal back and increase the power level. But when you do amplify that, you do end up with some ASD noise, as you can see, as it's transmitting down the line. And a real simple case here would be you would just demux that on the other end, and you would end up with the different channels with some noise from the amplifier. So this is a key reason why people would need to measure the OSNR in an optical signal. And seeing someone with a chat box saying no sound. Can everybody hear me?
Yeah, we can hear you fine on this end, Michael.
Okay. So hopefully you can resolve that issue. All right. Okay. So I'm going to jump into the definition of OSNR in this case, and in this explanation, its definition of the OSNR is a signal power ratio over the noise power. And that is a linear scale. And graphically, as you can see on the right, the signal power in milliwatts is defined as the peak power here at that wavelength, which is actually above the noise. So the peak power is the signal plus the noise at that wavelength as well as down here. And the noise power is defined as the noise level multiplied by what I would consider a normalization factor, which is a ratio between the reference noise bandwidth, which is typically about 0.1 nanometer, and the actual resolution bandwidth of the OSA. Okay. So with those two parameters combined, and in order to convert that to a dB scale, to a log scale, you would use the law of logs and divide these two and work out the equation to look like this, where you have the two components adding together. And so that's a very basic definition by the IEC standard of the OSNR. Moving ahead, and this is a really high-level explanation of it, and it's kind of funny. It reminded me of a case where the reason why I thought of this is one time I was talking to a friend of mine, and he was saying that I was telling him about looking at the noise-canceling headphones, and his first comment was, why don't you just turn up the volume and you don't have to worry about the noise? Well, I explained to him in this case, it's when you think of yourself driving down the road with your windows open, and when the windows are open, you got this background noise, and the music from your radio or the voice is going to be difficult to hear due to that air turbulence or background noise in the blue here as an example. You roll your windows up, of course, your music and background noise is going to all your background noise is going to get reduced, and you can be able to hear your signal much better. So that's you have improved your signal to noise ratio by doing that. So a common everyday thing that people can relate to, I think. So another thing that's very important is bit error rate for a optical transmission system. And the analogy I like to use is, as we know, the optical transmissions are transmitted as, pulses of light in general. So that's analogous to someone broadcasting or reading out a list of ones and zeros and ones and zeros. So you have a person on one end, they're reading ones and zeros, and another person on the other end is writing those down. So as you can imagine, you're reading those faster and faster. The person on the other end that's writing down ultimately might make an error once in a while. And if you have somebody in the background start talking, or if you roll the windows down in your car, you're going to get some background noise, and that person on the other end is not going to be able to hear your ones and zeros as clearly and as accurately, so they're going to start making more errors. So this is another fundamental explanation of bit error rate and why that's important to have to reduce your noise to be able to hear that clearly. And this is a more mathematical explanation of that. It's a correlation between OSNR and bit error rate using an equation from the IEC standard. So the equation is shown here, but basically the idea is that your bit error rate is basically a relationship shown where if you want to, say, achieve 10 to the negative 12, you would need to have a certain OSNR ratio as a slow speed test to at least get to close to that point. There's, of course, other errors that's additional factors to just OSNR, but this is a fundamental starting point to design your system. Okay. So how do we measure OSNR? So one very common tool is an optical spectrum analyzer. What is an OSA? Basically, it's an instrument to measure optical power in the vertical scale versus the frequency or the wavelength in the horizontal scale. So the power is measured in either DWDM or milliwatts versus a wavelength usually expressed in nanometers or terahertz in many communications applications. But what type of OSA is better suited for OSNR? Because there's multiple different technologies out there. So one very common one is based on a Turner monochromator. And the fact, the name in itself, mono is single, chromate is color in Greek. So the idea here is you have an input light coming in to this chamber, and it's reflected off a focusing mirror, and the light is still in multiple colors, okay? And the colors are spread out when you shine it into, when it gets reflected into a rotating grating. Okay, this is diffraction grating, reflects the light into a rainbow pattern. Okay, and that rainbow pattern gets reflected again from another mirror into a slit, and through the slit there will be a detector. I'll show you more details on that in the next few slides. And that's a basic principle of a rotating grating monochromator. A little closer look at the diffraction grating. I put it before. As some of you may have noticed, if you have a CD and you shine a white light on it, you could see kind of a rainbow reflection from the little tiny grooves on the CD. So closer look at diffraction grating basically is, that's what a CD, it basically has this little tiny grooves, and when you shine the light on, white light there, you're going to get a reflection in a rainbow pattern. And these gratings have very fine grooves, anywhere from 40 to 1,200 grooves per millimeters. Okay, and it's a reflective surface. It's like a mirror that has tiny little grooves in it. And that's what causes the diffraction. And this is an animation showing this concept where you have a white light source going into a grating, and that grating is rotated. So I'll start my animation with the next slide. So as you can see, as the rotation, as the grating rotates, the rainbow gets passed through this one slit. And keep an eye on, I'll run it again. So keep an eye on the trace on the bottom right there, where it's basically plotting the trace out, and that's what you would see on the OSA. So the light that gets passed through the slit will get detected with the photodetector, and that gets sent to an amplifier, goes to an A to D converter, and gets processed. And that's how it displays the image on the OSA. That's your trace. Now there's other principles. There's interferometer principle for an OSA. In this case, it's quite different than a rotating grating. In this case, you have an input light, and input light has multiple wavelengths here, and it gets fed into the Michelson interferometer. The Michelson interferometer consists of a beam splitter, and what's happening is you have an internal reference light source that has a known wavelength. It's a very high precision light source, and that's your reference light source. So if both of those, if you have the known wavelength light source and unknown wavelength light source, you shine that into a beam splitter. The beam splitter will split up the beam into two different paths. One is going into a fixed mirror, and it goes back into the moving mirror, so you're actually changing the optical coherence length as this mirror is moving. Now that beam gets, there's two separate beams, and it's detected by photodetector, two separate photodetectors. One is detecting basically the phase difference, the phase shift, when you're changing the length of that mirror by moving that mirror. And that provides interference signal between the two detectors in a time domain. So you can convert the time domain using a fast Fourier transform algorithm into a frequency domain, or in this case, wavelength domain, which is reciprocal frequency, to achieve your wavelength versus power. So similar result to the rotating grating, but very different technology used. So people might wonder, what's the key differences between the two principles? So I summarized here between a monochromator, OSA, and interferometer. Monochromator OSA in this case has a much wider range versus in this wavelength meter with the interferometer has a narrow range for telecommunications purposes. So that would work for most of the C-band applications, of course. But one thing to notice is the resolution is fixed on the interferometer, where it's adjustable on the monochromator OSA. Now, wavelength accuracy is a key here for the interferometer. The interferometer, based on that technology I mentioned before, provides very high wavelength accuracy. However, the trade-off is the dynamic range is not nearly going to be as good as the monochromator, and the level accuracy is not quite as good, and the level sensitivity is not nearly going to be as sensitive. So the green items here shown is what's really significant in being able to measure OSNR accurately. So this is summarizing the fact that you would need these key parameters to measure your OSNR. accurately. So of course, you want to measure your peak power accurately. You want to measure your low-level noise. You want good low-level sensitivity to measure your noise accurately down here. And you want to have a good close-in dynamic range. Okay, that's a characteristic of the monochromator-based OSA. And you want to have a variable resolution setting. And I will explain more of that in the next few slides. So I think the high power level and the low noise sensitivity is fairly obvious. You're measuring OSNR, you're measuring the peak versus the noise. And however, the other items, just want to clarify, if you have poor dynamic range, the base of the noise can't be measured very accurately. So this is showing where the waveform with a wide close-in dynamic range can show you the skirt or the noise level close to the peak, versus the other case where you have poor dynamic range, close-in dynamic range, you can't see the noise area very well, so you're not going to get a good example of a good measurement on your noise area. The other item I mentioned is wavelength resolution. So of course you want to have a high resolution OSA to be able to separate the signals, in this case to show you multiple channels in a DWDM signal or network, versus of course you have poor resolution, you're going to see one large spectrum and you're not going to see your different channels or your signals. So with that, in conclusion, we've demonstrated that a monochromator-based OSA is much better suited for OSNR measurement. So you would still need a monochromator OSA to measure your SMSR as well, besides your OSNR and also your bandwidth measurements. Okay. And so jumping into the basics of OSNR measurements, as mentioned before, this is a definition. This is showing a simple case of a continuous wave light, okay, where you measure the signal and noise power together, okay, using a single wavelength resolution setting. So in this case, it's fairly in a continuous wave light. You can virtually use any resolution. You can get an accurate reading on the peak power and your signal power together. Okay. Now, being able to measure your peak power accurately, as I mentioned before, you would want to set your resolution to have a wide slit. Remember I talked about the slit, and that slit actually is adjustable. When you change your resolution, you're going to change the slit size to let different amounts of light in. So in order to measure your peak power accurately, you want to set the slit to a wide, wide slit to measure that. Now I'll demonstrate that here, where you have a low resolution setting providing a wide slit to be able to measure your signal power correctly. It's fully detected here. Okay. And the resolution, and also it's important to note that your resolution is just enough in order to catch the noise area, so they're not overlapping. Okay, that's important. I'll mention more about that in the upcoming slides. The other thing is on the opposite side is if you're using a narrow slit, such as a higher resolution setting of 0.1, for example, you still get your peak, and you also notice that the resolution is enough because you want to use a narrow slit to be able to distinguish between your two signals that are closely spaced together. So, but however, no, that was the explanation of the CW light. Okay. Now, what if you have a modulated signal? Okay, so that was the CW light. It's fairly simple. But if you have modulated signals with the higher speed transmission systems shown here, different RZ, NRZ, dual phase shift keying, your signals are going to look quite different. So on the OSA, you need to make sure you have a suitable wavelength resolution in order to measure these signals. And I'll mention, why that's important. So this is showing a standard non-modulated signal, and there's a modulated signal shown overlapping it, the same signal that's been modulated. So what happens there is the peak power gets reduced, and it's only transferred to the side peaks. The peak power transfers to side peaks, so they're called modulation sidebands in this case. So in this case, before, when we were using measuring a CW light, the optimal slit size for non-modulated DFB was fine. But when we modulate that signal, it's no longer optimal to measure that laser because it's modulated. So that peak energy it's been reduced. It's moved to the modulation lines because it's broadened that signal. So that's the situation we need to deal with. So this is an example of different resolution settings on a modulated signal. So as you can see, this is a 10 gigabits NRZ modulation format. Okay. And the modulation has scripts at the 80 picometer bandwidth from the center wavelength. And the point here is that you would need to set your resolution to at least 200 picometer in order to get the full power measurement with the modulated light. So you need that wider resolution to capture modulated power accurately. Okay. And this is a summary of where that previous diagram where its modulation broadens. Okay, it broadens optical spectrum in the signal, and a narrow resolution. The peak is no longer measuring the full signal power, so you need to use a wider resolution to capture that peak signal. Okay, in this case, so the green is using a 200 picometer resolution setting. And then, of course, the spectrum varies depending on different types of modulation formats. Okay. And in the modulated light case, where we're talking about a single channel situation, okay, you have your peak here, okay, and then the resolution has to be wide enough to capture the full power, as I mentioned before. And your noise is down here, though, using that formula. But if you have a higher density or closer space system, as people are moving towards faster and faster and closer spacing in the DWDM signals from 100G to 50G to 25G, your spacing of your signals starts getting closer and closer together. So that presents another problem, where when you're using a wide resolution to measure the full signal power, you're getting that power, but what's happening is you're missing the true noise. The expected noise is down here, but the signals are so closely spaced together that the notches are not going all the way down to the noise floor. So therefore, of course, you're going to not have an accurate OSNR measurement because your noise floor is basically getting they're overlapping each other. Okay, so here's an animation of that situation where you have the 50 gigahertz spacing. Okay.
and you have the correct noise channels between the channels. In this case, if you're using the proper resolution setting, whereas the noise points between the channels, if you're using a low resolution, is not going to be measured accurately. So the solution to correctly measure that situation for modulated DWDM signals is to use the low resolution setting for the signal power and a high resolution setting to measure your noise. Okay, so you really need to have this dual trace or dual resolution method to measure your OSNR accurately, because you need to get your peak power accurately with the low resolution measurement, and you need to get the noise accurately, because otherwise your noise is here, and that's, of course, not going to give you a proper OSNR reading. Your noise is actually, your true OSNR values should be from here to here. So you need to perform two different sweeps in order to get this true OSNR reading. So there's automated methods to do this. Okay, so this is a result. Most telecom OSAs will offer built-in single trace resolution, so fairly simple, where basically you press an easy button, or automated button that's built in, and the results are showing the trace with the peaks, the noise, and a summary table underneath showing the different peak wavelengths of each of the channels, the offset, and the noise here. This is the OSNR ratio that's being calculated. So that's using the basic single resolution method. If you want to use the dual trace resolution method, as I mentioned before, there's a setting you can change in most telecom-based OSAs, where it takes a signal measurement on trace A, for example, on the first trace, and that's measured using a low resolution. So in this example of an NRZ signal for 10 gigabits per second, you might want to use a 0.2 nanometer resolution, or for 40 gigabits, you might want to use a 1 nanometer resolution to get your signal measurement. Now for your noise measurement, you want to use a higher resolution on trace B, and this is done automated by the instrument itself when there is that feature. And so simply go to the menu that allows you to select that. In this case, there's a checkbox, and it shows your dual trace, where you can just select that before you execute your WDM analysis, and it should give you the correct signal-to-noise ratio for a modulated DWDM signal. And so that makes it quite simple. And this is just showing the dual trace resolution method on the screen, where it's got measuring the peak correctly, okay, using a low res, and then you're measuring your noise correctly in the purple. And that's how it's doing the same calculations, but it's being calculated from the two different traces that it gathered automatically in the routine. Okay. So in summary, wanted to just note, while the infrared OSAs offer very accurate peak wavelength measurements, monochromator-based OSAs are much better suited for OSNR measurements due to the high peak power accuracy. Pretty obvious. You want to measure the peak power accurately, and of course you want to measure the noise level accurately, so you want to have a low level sensitivity for that. And you want to have a good close-in dynamic range. As I mentioned earlier, you have to be able to measure the skirt of the noise close to the center wavelength. You ought to have the variable resolution settings in order to change your resolution to measure your peak and your noise level accurately. And you really need to change that in order to get those two. Otherwise, you won't be able to see that noise that's getting overlapped if you don't have that, if you don't change that setting. Next item is the OSNR value is a low-speed predetermination of the burr performance, so you definitely want to make sure your OSNR is close to your spec before you can expect a system that will perform to your bit error rate specification. And the error rate is, of course, very crucial to offer a reliable transmission network. You want to be able to get all your ones and zeros across to the receiver accurately with minimal errors. On a multi-channel modulated signals with overlapping noise floors, a normalized noise value is required to calculate the OSNR. That's using the B sub R, B sub M normalized ratio, and that's defined by the IEC spec. And as mentioned, the OSNR, the modulated DWDM signals requires a low resolution setting to measure the signal power and a high resolution setting to measure noise power accurately. So that's the key behind the dual trace method. It needs to be specified and activated when you're doing the automated routine on the OSA setting menu. Okay, so with that said, I'm going to open the floor to any questions from the audience. So one of the questions is, when using one of your OSAs, AQ6370C and D model, do I need to activate the resolution correction when using the automated WDM measurement? Okay, yeah, that's a common question. The word resolution correction is a little bit misleading. It's not required to be activated when you are using the automatic OSNR measurement or WDM measurement, because that measurement, the algorithm automatically compensates for that resolution setting. Okay. And another one is, why are the OSNR results from the Yokogawa OSA QDB different than another OSA I've used in the past to test the same device? So that could be a couple of things. It could be possibly due to the resolution setting causing incorrect noise level, as I mentioned before, between the two OSAs. So, refer to the suggestions I mentioned before for, like, for example, the 10G or 40G signals. Could also be due to the difference between the N sub I subtraction. Remember the slide I mentioned before showing the, you need to subtract the N sub I, the noise from the peak power before you do the OSNR calculation, based on the latest IEC method. That's the, maybe I can back up to a slide that shows that the N sub I, make sure that you add this to your peak power signal. I'm not sure you're measuring that manually, but that's, of course, very important to get your OSNR value to match with the automated results from our OSAs, or from the OSAs that are using this method. So it depends on if you're using a manual method or using an automated method. Okay. Let me see. Go back to questions here. So another question was, does dual trace measurement take double the time? Yeah, you do have to measure both traces, but if you actually try this in real life, it's, you know, the OSA and at least the current models are quite fast, and it's funny you mentioned double time because there's actually on the Yokogawa OSA there's a double speed mode where you can click on where you're using a high sensitivity setting. It actually will literally double the speed of this sweep. So in different cases you may need to set the sensitivity to a higher setting, but there is a 2x mode on some on our units, so some depends on what you're using, but yeah, in reality you will need to take 2 traces. So linearly speaking, you would have it would take twice the time. But of course, you want to do you want to have accurate results. So, you know, that would be a trade-off. It would be meaningless if you did it with 1 resolution and you get the incorrect result because it's not measuring the noise level correctly because of that overlapping signal situation. Okay. Yes. Let me see what else. I think can measure in-band OSNR with your OSA. We've been monitoring this situation, and unfortunately, we are not aware of a commonly accepted standard results from industry yet. We've been hearing people have using different suppliers to measure their in-band OSNR, and they're finding that they're not correlating with each other due to maybe it was designed, those instruments were designed before, not reference to industry standard for that in-band OSNR measurement. So we felt that wasn't appropriate to offer another solution without the general consensus agreement from the general industry on the in-band OSNR measurement. Okay, so I think it's not practical as a supplier from the supplier perspective and for the industry as a whole, I believe. So I think with that said, we're getting close to the mark where we need to sign off, but if we have further questions, feel free to email me directly, and I'll try to get to the questions, the other questions I couldn't get to that were brought up during the presentation. So thank you very much, everybody, for your time, and appreciate you joining us today. And again, let us know if you have any questions and feedback, and hope everybody has a good day or a good afternoon, wherever you may be.
Thanks, Michael. Thank you, everyone, for joining us today. And as Michael said, you can always reach out to him directly there, or you can reach out to us at webinarwednesdays@us.yokogawa.com. Make sure that you submit us any questions you have or any feedback. When you close out WebEx today, it will bring you to a survey. If you could just take about 1 or 2 minutes, fill that out, let us know what you thought about it. And please look forward to any other upcoming webinars. You can check us out on tmi.yokogawa.com. Thanks, everyone. Have a good one.